and then following that, you can see a picture of me. So this is me, and I would just start off with a question. So I've been in computer science for almost 30 years now. I hate to think of it that way. And I was just wondering if people knew what question I get most of the time when I'm walking around campus. I'll let you think about that for a second. Think about what people might ask me in my daily existence. I'm gonna take a sip. I've learned to take a sip when I ask a question in class. Well, if you guessed, are you with the football team? You would be correct. That is what people ask me the most, and I usually respond to that by saying no. And have you seen how big those guys are? So if you actually saw me compared to, like, real football players, it's me when I played rugby in graduate school. You can't see it now, but I'm a reasonable sized guy, but I'm not as big as the guy that you watch on TV. And so if you wanted to ask, then what question do I get? What's the second most question do I get when I'm on campus? That would be, when will I graduate? So I just turned 46 this year, so hopefully I don't get that question. Maybe I'll still get that question, I don't know. But I usually respond to that by saying I'm actually faculty in computer science. And what I work on, what my research is, I program autonomous robots. So the kind of robots I'm thinking about here, this is a picture with a robot that I used to work with, which is the Willow Garage PR2. These robots are capable of moving around autonomously in space, increasingly capable of manipulation, dexterous manipulation. So working with objects, handing them over, assembling structures, doing all sorts of great things. And so, this is really, today we buy robots and then we program them, so sort of like what we do with computers. And so, we bring a lot of kids in for outreach, and usually the question they have for me right after they see that is that a real job? To which I have to say yes. It may not have seemed like a real job to me when I was 16 as well, but yes, it's increasingly trying to show kids what opportunities are out there. And that usually is followed by a variety of other questions that are out there. Are you making R2D2? Will robots be our friends? All sorts of things. But in this talk, I want to focus on three questions of interest. One is, will robots take over the world? Where is my robot, and can your robot bring me a drink? And so let me take the first question. Will robots take over the world? And the reality is, I hope people in both robotics and artificial intelligence continue to say this, robots are not nearly that smart. Science fiction has filled your heads with all sorts of great dreams. We're not even close to there. And because we are the creators of technology, we can also decide what they will do. And so we can create robots that will help humanity. And I think that can be one of our goals. One thing that we do when we decide what the technology will be. So for instance, I gave a TED Talk a few years back with a former collaborator, Henry Evans. And so Henry, he suffered a stroke-like event around the time that he turned 40, and it left him without the ability to move on his own and without the ability to speak. And so he relies on others to do his tasks of daily living. And so that level of independence is something we oftentimes take for granted until we lose it. And so what one of my colleagues at Georgia Tech did, so one of my colleagues, Charlie Kemp at Georgia Tech, he took some of the work that we've been doing in terms of making network protocols for robots and web-style user interfaces, and he took those ideas and started creating interfaces for Charlie to be able to use a PR2 robot to be able to do things for him, to be able to do activities of daily living on his own, like being able to scratch an itch on your face. Imagine if you couldn't do that. That would kind of drive you a little nuts. That's Charlie in the background there watching Henry shave himself for the first time in about, I think, 11 years. And to give somebody the ability to do things on their own was an amazing experience. It is one of the most inspirational things I've been able to do in my career. And so what we're able to build from that Can just a quick check. Can you guys see? Are you able to see this video? I just want to make sure I'm sharing the right screen.
We're seeing a still frame at the moment.
All right, cool. I just want to make sure that you're seeing a still frame of Charlie and everybody. So, all right. So I'm going to move on. And so what we were able to do with that with that is really trying to make robotics accessible to the masses through web technology, but more importantly through network protocols. And so the idea is that we were trying to make a TCP-like interoperability for robotic systems. And so we created something called the Rossbridge networking protocol, which meant to be minimal, simple, general, so that all the great things that are happening in artificial intelligence or human-computer interaction or other areas could then have a seamless way to work with a wide variety of robots. That level of interoperability, I think, is key for one principal goal of my lab, which is to bridge high-level artificial intelligence with the low-level systems of robotics, and so the methods and systems that we're trying to do. And so one thing that we did with Henry as well is, one of my colleagues at Willow Garage, where I was working at the time, said that that Henry wanted to fly, and could we make that happen? So I said, we can make that happen. That's pretty easy. So I went down to the Brookstone. I bought an AR drone. We wrote a driver for the robot operating system to work with this system. Using Rossbridge, I created a very simple user interface where you can see from the camera on the drone, have nice big buttons so that Henry could control it, because the only thing that he can do is really you move and click on a mouse in a display using assistive technologies. And from that, we just took it up to Henry's house and we saw what he could do. And so this is Henry's first flight. The drone that he's controlling outside was in the red circle there. And Henry was able to just start flying right away. And it was amazing. He was able to go off and inspect everything around his house. He looked at the solar panels that were on his roof that he'd never been able to see. He went and explored his garden area because he watched, looking at some of the things that they were able to plant. And so being able to restore motion to somebody and give them a greater sense of independence through robotic technology, I think is just, there's really few words to describe the feeling the sense of fulfillment that we got from that. And I think this is really just one of the things that we could do. There's a wide variety of robots that are coming out that as somebody who's working in artificial intelligence, you shouldn't necessarily have to worry about the details, all the low-level things. The same way that an operating system provides a hardware abstraction layer for you to work at the applications layer and then be able to instantiate it portably on many different types of robotic systems. That is something that we're trying to do right now. And that's something that should be a feature of robotics, especially as it comes together with AI. And so when I talk about these types of systems, usually what kids say or other people say, that's cool, that's awesome, inspiring. Is that like Silicon Valley, that show on TV? And usually all those questions are followed very quickly soon with, so where's my robot? Where is the wait a second. So let me. So I usually say that your robot. So if you're looking for your robot, it's actually here. So the types of robots that you're thinking of, the ones that you remember from, Rosie the robot from the Jetsons or those types of systems, they're actually being produced right now, as well as drones and autonomous cars. And so if you think about the kinds of robots that would be the PR2 that, as I mentioned before. But the first purchase that I made when I got to the University of Michigan in 2015 is I bought a Fetch mobile robot. And so with these robots represent sort of what we have now, but also are sort of visions into the future of what the types of robotics that you're going to be able to use in your own work, but also be prevalent across society. The question I would ask I would put to the audience here is think real quick about how much these robots would cost. How much do you think these robots cost? How much is the PR2? How much do you think the fetch robot is? I'll take another quick sip. What you think about it? Well, the answer I will put in graph form is that I bought the Willow Garage PR2 came out in 2009. I bought mine around 2011. It cost about $400,000, which is a lot, which can be a lot more than some people's houses. The fetch that I bought in 2015 was $100,000. And if I compare that to the first robot that I worked with, which was the NASA Robonaut at Johnson Space Center, NASA will not tell me how much that robot actually cost, but my guess is around 1.5 million. There we go. Somebody guessed 2K. 2K is way off, but I appreciate it. Someday 2K. Thank you, Ruben, by the way. But if we think about these data points and we remember our ability to fit polynomials from linear algebra, I think what you're seeing is a trend line that looks like this. And with that trend line, I would say that your robot is here in the year 2020. I originally made these slides in 2018. And I think you're already seeing some robots of those forms. So there's Hello Robot. There's a number of other robot systems that are sort of around the 40K range. Some are less, some are a little bit more. And what you're also seeing is the economies of scale. I believe the Robonaut, there were about 3 or 5 Robonauts built. There were about 60 Willow Garage PR2s. I'm sure Fetch is in the hundreds by now. And when we start to see these robots start to get cheaper and cheaper, we're going to start producing them by the thousands or maybe the hundreds of thousands. And so that's what we're seeing in terms of this curve. But also, it's not just the robot itself; it's about how we control the robot and the autonomy that goes on board. So, for instance, back when I started as graduate school, everything was done through remote control, teleoperation, and so that meant the human was doing all the cognitive work, and really the robot, you just exchanged your body for the robot's body in terms of carrying things out. With the advent of all sorts of great sensors, we had essentially put their level of autonomy. That is, how do I take something from point A and bring it to point B? How can I how can one of these objects pick up something and then move it to a new location? Autonomous driving is really about putting you there in a new position. And where we're moving to is where we can have a robot do this task for me. So so it's not just a single action of put something here, but really execute a sequence of actions towards reason, where you're reasoning towards a goal, and that goal essentially is some outcome that you want in the world. And so that's where we're sort of where our current challenges are in robotics. And when I say do this task for me, what we really mean by that is how can we make your world programmable? Digital computing has made information programmable, the automation of information, but how do we extend this out to the physical world? And so when we think about that, we think of the type of robot systems we're looking at and the types of environments that they're going to face. I just took a random image off of Google of a kitchen and somebody cooking their dinner, it looks like. There's a lot of uncertainty. I think even some of the best neural networks systems right now, recognition systems, can only recognize a fraction of the objects that are here. And understanding the semantics of what you can do with these objects is still a challenge. Still is a pretty open problem. And so these environments, the common human environments, are really still unknown territory for how we can get our robots to reason and execute well in these types of environments. And if I had to state what the goal is that we want of these systems, is that we want to be able to have, that we want to have software systems, AI systems that allow us to take any arbitrary robot and make it capable of performing any arbitrary task in an arbitrary environment. And that is really what we're after in terms of our research, but I believe what we share in common with the ACS community. Typically, this is expressed as the problem of learning from demonstration, and so that build happened a little too fast. But learning from demonstration is how we have how we can teach our robots how to do things, and he can learn from our experience or from our guidance. The first system that came to mind when I think about learning from demonstration is the MIT AI Lab copy demo from back in the 70s, and that was led by Patrick Winston. And so the idea of the copy demo is that you would be able to demonstrate a scene, show like, this is what I want the scene to look like, and show that to the robot. The robot would be able to perceive that desired scene that you've laid out, and then be able to reproduce that scene. So in this case, you have a robot arm that can see the scene on the left, take the 4 bricks that are off to the side, and be able to reproduce that scene. Obviously, a blocks world doesn't represent a real world, and so even though this represented the essence of a lot of things we're trying to do in learning from demonstration, it took a long time to get the computer vision and reasoning and robot manipulators to be able to do this in sort of real environments. And when I think about this phrasing of learning from demonstration, it fits in a larger context. So I had the pleasure of writing a interactive task learning paper. So John led this, and and I think it provides a great context for how we think about the types of learning systems that we want to have. And it expressed the concept of the ultimate interactive task learning system. So to make taskable systems. And so we could look at this from the perspective of how well can our systems perform tasks, how do they scale to new tasks with different types of knowledge, and what's the ease of interaction, and expressing those in 3 axes. And so there's trade-offs on a number of different approaches, including cognitive architectures, traditional programming languages, and learning from demonstration is my typical sort of background for looking at this. But I think there's opportunities to do new things that will be even better. And so one of the things that I have been trying to do is think about learning from demonstration, not for what it is right now, but what it could look like in terms of its next generation. And so moving it, so I think of it sort of almost like sliding along the scalability for new tasks, probably even moving it up in terms of the ability to do task and performance. I'm not a usability person, so I know very little about the ease of interaction. But I think there's opportunities to move us closer and closer to the ultimate taskable learning systems. And so with that, I think when I think of next generation learning from demonstration, I think of what we could do in terms of semantic mapping, that is providing semantic perception over 3-dimensional space, so that we understand, so robots can map out their space, understand what objects are in that space and what affordances are given by those objects, so that we can start to understand how robots can act on objects, and combine that with planning-based programming, so that you have ways to reason towards goals and be able to express those goals. And the combination of these is sort of what we're thinking of the next generation as what we're calling semantic robot programming. And so, taking inspiration from learning from demonstration and the copy demo, we'd like to be able to just express to a robot, this is what we'd like for a scene to look like. And so here's just an arbitrary scene. Be able to use those by perceiving objects, so using combinations of neural networks and probabilistic inference, to be able to infer the scene graph that we see in the world and express that axiomatically. So if we can do that for our goal scenes, then we can also do this for them. If we come into any arbitrary environment, we can then use these same perception systems that combine generative and discriminative inference, be able to express the scene graph, and then use a lot of the great work in classical planning, as well as recent advances in AI, to help our robot transit the current scene to any arbitrary goal scene. There are some limitations in the current work that we're doing here, in that it's still thinking about pick and place actions. We're not necessarily, it's current work to think about the different types of affordances that we have. Don't ask me why we would want to put sugar and sunscreen and bleach on a tray. I think that's part of the arbitrariness that my students wanted to put on there. But starting to think about this in more purposeful ways, so that we can think about the context that the robot should have, the physics that's involved, other types of things that our robots could function and understand what we need from these types of worlds. We've run this many times, and so we're able to work in a variety of different scenes. And even these objects are still these configurations are still relatively clean. We work in messier environments too, which is why we start to think about, and for the sake of time, just trust me that our robot works well in these cases. But if we wanted to start thinking about how we could work in real worlds, we start to think about perception in terms of scene estimation and clutter. That what we want to be able to do is assume that we have we want to assume that we have object geometries for now, even though that's not a limitation of the work in general. But we want to be able to infer the scene graphs needed to provide axiomatic representations to AI systems. And we want to be able to do this in the face of all sorts of uncertainty due to occlusion, stacking, different types of contact configurations. And we want to do this in a way that eliminates a lot of the crutches that we've had before in terms of green screens, AR tags. I think we can do much better. And we take inspiration from the great work that's happened in autonomous navigation. If you look at the types of robotic systems, such as the ones that my colleagues Ed Olson and Ryan Eustace here at the University of Michigan have done, they're able to build fabulous 3D models of the world. So just using the laser rangefinders on top of their autonomous car, they can build maps of Ann Arbor that look absolutely beautiful. The football stadium that we're not going to be able to play football in this season. The downtown area that we have to be socially distancing right now. Those are these types of environments. We can build the geometry of these environments really well. The problem that we face is that we don't know the semantics of this environment. We don't necessarily know which points of these geometries belong to a tree versus a building versus a car versus a pedestrian or the roadway. And so all of these make a really big difference because you want to treat those differently. You want to act around those different types of environments differently. You want to be able to note that those bicyclists going through the intersection, we really don't want to hit those people at all. And so what we're doing is we want to be able to think about goal-directed, the same way that we think about goal-directed navigation, we want to think about those for our mobile manipulation robots. And so if we think about the ways that we do navigation, typically our localization is probabilistic because we have partial observations of the world, and so and it's full of uncertainty, so we have to maintain many different hypotheses about what our interpretation of the world is. But from that, we take an estimate that is our best guess at this time. We give that to our planning and control systems to execute, to do the navigation towards the goal, and we do this in a closed loop over and over and over. We would like to do the same thing for goal-directed manipulation, where we have probabilistic approaches to perceiving the scenes, and then we take our best estimate, and then we're going to plan and perform control using that best estimate. And even if we're wrong, even if our estimate is wrong, the world will change, our probability distributions will shift, and then we'll hopefully get a better estimate that's more reflective of the world as we continue to act. And so one thing that we do in my lab is we do address the scene estimation problem. And so one method that we have a number of different pieces of work, but one I'm really proud of is our sequential scene understanding and estimation, scene understanding and manipulation, SUM. And so in this case, what we do is we have our robot be able to see the objects in the environment, and then in this case, what they're doing is sorting it into laundry and not laundry items. So the Downy goes over into the left bin because it goes in the laundry room. The pool toy goes in the right bin. It just put the Comet into the laundry room bin. That is a mistake, but it's not the robot's fault. I don't think my students really do a lot of laundry, so they didn't know that the Comet goes in the kitchen and not the laundry room. But once we do this, we can essentially sort these objects. And the way the perception system works is that we use a neural network to give us first guesses about what objects might be in the scene, and then we use and we enumerate all possibilities of what objects could be seen, the objects that could be in the scene, and then we use probabilistic inference, generative probabilistic inference, in order to figure out what's the most likely configuration of the scene, and do inference over those and try to do it as efficiently as possible. And then we can start to remove false positives, and some of our recent work remove false negatives, such that we can then localize the objects in the scene and then take a reasonable action. And so that, so one thing that we're aiming for with a lot of this work is to try to combine the recall power, the speed and recall power of neural networks with the robustness and of probabilistic inference. And so that really is something that we're trying to do. Because just to be honest about it, I don't trust neural networks completely, but I do realize that they have a lot to offer. And so with semantic robot programming, we have a number of challenges that we still face. One is being able to incorporate context and physics, because if we're trying to do probabilistic inference, it is really slow. And so we've been working on things like non-parametric belief propagation, some of our recent papers, and being able to do this quickly and be able to make probabilistic inference at least a reasonable, put it on a level playing field with neural networks. And I think that could have, think of this as a general sort of inference tool. The types of environments that we're thinking about for humans are dominated with clear objects, translucent objects. And so how do we start to think about recognizing these types of objects and then being able to estimate their pose so that robots can take action on them, as in the video that you're seeing over to the left. And so some of our recent work thinks about that. We're venturing into thinking about affordance representations and how we can do planning and control over affordances. And so we've had some work in those areas. If you've noticed that our current definitions of semantic robot programming are very much like the copy demo. We show a scene and then we try to reproduce that scene. But I think if we want to think about multiple different types, if we have multiple demonstrations, how can we infer the goal conditions from those user demonstrations across that's common to all of those demonstrations? And those and so I would specific to general to specific inference, or specific to general inference. Some of John's old work comes to mind there. We're taking different approaches, thinking about this as factor graphs. And that's work that's going to be coming out soon. And we were fortunate enough to win a Best Paper Award for going beyond the tabletop and thinking about new ways of object permanence. Because our robot isn't going to be able to see everything all the time. Our robot will have to maintain some belief about objects it can't currently see, so that it can reason if it has to, in order to accomplish a task that might be at the building level or even the city level. And so that's really sort of where our research agenda has been going. But I think, as John said, I think about the larger implications of our work. And that makes me think about the next question, which is, can your robot bring me a drink? And whenever roboticists think about drinks, we think about beer. And so, can your robot bring you beer? And, the answer to that is sure, no problem. We've done that a lot throughout my career. So it seems like robots bringing drinks to people is just a common thing that just gets done all the time. And when we do demos of this, that's usually, at least recently, that's usually when we get asked, have you seen Silicon Valley, right? They saw the robot episode with Silicon Valley, or they see a lot of tech stuff. And, and in this show, which is a great show, if you haven't had a chance to see it, I highly recommend it. Although you may have to it's a little crude, so you have to be ready for that. But in that, you have a lot of, in that show, you have a lot of Silicon Valley entrepreneurs that say that their work is making a better place. They're, whatever they're pitching, whatever they're extending out in terms of their company or whatever their work is, it's making the world a better place. For instance, you're making the world a better place through constructing elegant hierarchies for maximum code reuse and extensibility. That's Gooly Bib right there. Or at TechCrunch Disrupt, you had the fictional TechCrunch Disrupt. They're making the world a better place through scalable, fault-tolerant, distributed databases with ACID transactions. Or my personal favorite, which comes through Hooli, which is the big conglomerate that sort of has taken over it, and probably would have been at the congressional hearings a week or so ago. The CEO of this fictional company basically said that Hooli is about making the world a better place through minimal message ordering transport layers. And when I heard that, I was thinking to myself, am I, that sounds a lot like me. Am I, if you replace Hooli with Rothbridge, which is something comes to my group, then I mean, you could very easily be talking about me, and I'm, you know, I'm making the world a better place. I sound very much like these characters that are being parodied. And so it brings me to think to myself, will my work actually make the world a better place? I think about this all the time because I love the science of what I do, but, you know, but I also question, what's going to happen with this technology as it's developed? Am I training my students the right way? And all of this came together for a lot of people in the community. It came together on May 25th of this year, Memorial Day. A lot of people talked about, saw what happened to George Floyd. It gave us a lot to think about as a society and what we're doing. And, you know, and I was part of a group that wrote a letter, an open letter from blackandcomputing.org that talked about the things how a lot of us in computing, a lot of the Black scholars in computing feel about this situation, and things that we think that could happen to affect systemic change, and so that would be good for our field. But these things are still relatively abstract. You know, how does George Floyd connect to what we do in computing and AI? And so it's sort of sitting out there, but it got very real later in the summer when we were thinking about when the revelations of what happened on January 9th of this year happened. January 9th is my birthday. I turned 46 this year. And when I think about what happened, the revelations came out that Robert Williams, who's not far away from Ann Arbor, where I am right now, he's in Farmington Hills. He was falsely arrested, purely based off of a facial recognition hit. And so so basically there was a facial recognition hit that was used by the police to identify him from a burglary that happened. And so, you know, so the question is that person that's in this grainy footage here, is that actually Robert Williams who you see here? And it was not. And so, the painful aspect of this that happened is that he was arrested in front of his family, his small children, his neighbors. He was detained for 30 hours. He was, I think they may have finally cleared his record, but he was one of the people but he was fortunate enough that his case got a lot of attention. I worry about that there's other cases like this that are out there, and he's having to say things to the AI community that we should have known about the use of our technology, and having to educate us about what we need to be doing. Because really, I think all of us sort of know, if you were to put your own life that rested on being able to take a grainy photo image and that would determine whether you were able to live your life free or not, I don't know if we would trust a neural network to do that. And we even saw early this early this summer, that work that came out earlier that you could take a grainy small image and turn that in and reconstruct a high resolution image, but it's very susceptible to problems. So as in this grainy footage of President Obama that got turned into a Caucasian man, that was not quite right. And in addition, I think some people in our field, such as pioneers who have done excellent work, like Jan LeCun, sort of still are saying that, well, the issue is not necessarily the neural networks itself, it's the data that you use. But the problem is that we just don't have the right people in the room as we're constructing these systems. When we're thinking about when these systems are created, it feels very much like there are many different demographics that are not present, that don't have a seat at the table, that will have an impact on all of society. And so this motivates the need not to just think about the explainability of neural networks, but also the need to have greater diversity in our field, because if we're successful, our work is going to have a huge impact. Even in my own field, if I look at the International Conference on Robotics and Automation, deep learning is by far away. If you look at the number of papers, number of authors, deep learning is by far away the most subscribed topic amongst published papers. And that is a recent happening over just the last few years. And so I think we put too much confidence in these systems. And I would say that AI has really failed us systemically. And I think we can do better. When I look at so the issues of how AI behaves, we have AI research like myself and people who are listening here. And when we look at the AI research community, we have few and marginalized Black AI researchers. And so I just took example of this. So this is from Viola Jones, 2001. The early facial recognition systems that are no longer used, but still provide a lot of inspiration. Similarly, that AI research feeds into systems development, where we have low production of Black people with CS degrees, and that so there's very few people to enter the workforce and help provide the wisdom that's needed to develop these systems the right way and produce the right training data. Similarly, once these systems are developed, the end use, we don't necessarily have a fully educated use of this technology by law enforcement and other types of, and law enforcement is just one example. There's many different areas across the society that are at issue. And so across this pipeline, we have not necessarily included Black scholars, engineers, executives into this discussion. And I would say that there are many different types of problems. So if you want to think about the front end problem, there's great work in algorithmic fairness community, such as by Joy and Temnet right here. Their work from 2008, which I think talks about the issues of using facial recognition in the world. But what I know as somebody who's faculty in an excellent department, excellent computer science department, is that we also have a back end problem. I'm proud that Michigan this year has produced its annual diversity, equity, inclusion report, and that really starts to think about how we can get more people, create equal opportunity in our research labs and our classrooms. I wouldn't blame Viola Jones for our problems. This is really a systemic problem. It's not necessarily researchers. It's really about how we incentivize and practice artificial intelligence. And if you go back to Viola Jones, they had a wide diversity of people in their original paper. And so I think I don't blame we don't blame the research. We sort of need to look at our systems. And so we've just failed to include Black people in the advance of AI. If we look back to a fabulous book by Nils Nilsson, which was The Quest for Artificial Intelligence, which goes back and name drops all the people who played a huge role or a significant role in artificial intelligence. There are just no Black people cited in that, and I think that just breaks my heart. This isn't just the issue of the past and the history. If we look at the numbers of the diversity in the workforce, it doesn't look quite good, and it's really what we call a disparate impact. That if you look at African Americans, Latinx, female participation in the tech workforce, it is way down from the representation and the population. And this is really saying that maybe our systems aren't doing a good job of providing that inclusion. And that inclusion has a huge impact on how the lack of diversity in our systems leads to software and systems that have these biases. And so the question that I would pose to the community or that usually the community poses to me is, how can you be a better citizen through AI and robotics? And I would argue that this is that you should understand what drives the system. If I was thinking about how I work, this is not the hate the player but hating the game, I guess. This is if I want to think about what incentivizes us to get things done, forgive the noise in the kitchen for a second, is that what we do is we create an image of ourselves that appears successful. We use that appearance and our gravitas to get money and get and get the support to produce results. We come together as alliances of like-minded researchers, and we do a form of collusion to promote the views of our alliance. We also, I worry that the peer review process is not very good for having good debate between individuals. between scholars. And so I think it's a little passive aggressive, and I think it puts off a lot of minorities. We use what we've built up to build our patronage, to get our people placed in positions of influence, and then we use that patronage to get more funding, more people, and then we rinse, wash, repeat. And this is really no different than what's being asked of law enforcement. That law enforcement, it does the same things, the same cycles that we use that solidify sort of dogmatism and research also applies to what's being asked of law enforcement right now, in terms of rethinking and reforming. And in some cases where it's gotten out of control, defunding. But those are systemic issues. What can you do as an individual? Much of this talk came from what I gave to the Robotic Science and Systems conference back in 2018. And so and that talk is online if you want to see that one too. And really it's summarized in this, that what you should try to do is eliminate the double standards in what you do as an individual, what your organization that you're part of does, eliminate double standards organizationally, and also in your community. And the way you do that is by thinking about how are you consistent in the treatment of your colleagues, your students, people applying to be a part of your programs. When you look around, how intellectually diverse is your research lab, your citation list, your classroom, the committees that you've served on? And if you can eliminate double standards in those dimensions, you can eliminate the disparate impact that we have in the field and help us bring equal opportunity, realize equal opportunity. One thing I forgot to say in there is how diverse is my funding review meeting. And so if if I just wrote a piece for VentureBeat that talked a bit about funding. Funding is really where the rubber hits the road. It's about, I think we all want to do the right things for society. We want to have diversity, but we have to be able to invest in it. We have to be able to give money and funding and that level of support. And so one big thing that we can do is incentivize equal opportunity in computing. And this is something that doesn't require massive amounts of legislation. We don't have to necessarily march in the streets to get a legislation passed, because that legislation is already there. The Civil Rights Act of 1964 prevents discrimination, if I'm only speaking the American context right here, but American Civil Rights Act of 1964 prevents discrimination by government agencies that receive federal funds. That means if you are not producing equal opportunity in your organization and you're receiving federal funding, you're probably not in compliance with the law, or at least the spirit of the law. We oftentimes see this in terms of Title VII, which says that you can't discriminate you can't hire or fire somebody based off of their particular race, color, religion, sex, or national origin. So that's on the sort of the input into the system. On the back end, you have to produce equal outcomes, and that's what this says. I know that my story in computing would not be possible without Title IX that came out in 1972. This is President Nixon signing it. That created all sorts of great opportunities created equal opportunity, or at least the foundation for equal opportunity in higher education, where anything that was available to men also had to be available to women as well. That's why you have a women's and a men's basketball team, and vice versa. And I think it also had an effect on AI and computing, which allowed for many of the mentors who provided me guidance throughout my career, many of the female mentors, to be able to have a place and have an opportunity in computing. I would love to say that President Nixon is signing Title IX here. I could not find that. Actually, this is him signing the Clean Air Act in 1970. I believe there were many things going on in the White House at the time Title IX was signed. But overall, what I would argue that in the computing and artificial intelligence, we need to have more empathy in the work that we're doing. Our work has real consequences. We make amazing strides, but we also have to think about who is there as the technology is being conceived and developed, and that will help us achieve better outcomes for the technology once it's out in the world. And so the last thought I would leave you with is that when we think about our work, we usually think about innovation and excellence. That is what drives me more than anything else. I want to do work that's amazing. And what I'm asking for is that you also consider equal opportunity as part of what we're doing on an equal footing with the innovation and excellence. And both of those things have a foundation in terms of the economic incentives that support us and give us the motivation to do what we do. And so when we're thinking about trying to be at the intersection of all of these, of being excellent in our work, creating equal opportunity, and being viable economically, there's things that we can do, and that's what I've talked about in this presentation. In terms of innovation, I think there's great work that we can do to realize semantic robot programming and build a better bridge between AI and robotics using messaging protocols to bring everybody together, interoperable messaging protocols to bring people together. I think we can eliminate the disparate impacts in our field and realize equal opportunity, but that requires modernization of how we support and fund individuals in our field, the work in our field. And that I think requires a modernization of Title IX to be broader, but also including the spirit and the statutes of the Civil Rights Act of 1964. And so with those comments, I'm done. I think I'm just at 50 minutes. So I just wanted to thank everybody, and I'll take any questions.
All right, Chad, this is John. The way we're going to work questions is that people have put questions into the Slack channel, and I'm going to read you a few.
Okay.
And we'll go through them. The great thing is that after your talk at 10:30, I'm sorry, at 9:30 Pacific time, we're going to switch to the poster sessions, and there's also going to be a chance for you to have interactions on a Zoom channel, room number 5, for everyone, starting at 9:30 Pacific time.
Okay.
So let me start with the first question from Matt. Any robot to do any task in any environment is a massive goal. When you work on learning from demonstration for a diverse set of tasks, I assume you're going to fix the environment and the robot. How do you ensure that the things you are learning about designing systems that learn from demonstration will have the right representations to operate in different environments? Whew.
Right. I think that's a great question. Thank you for answering it. And I believe that with the perception capabilities that are arising, we will be able to work in a variety of different environments. We will be able to, we won't have to fix the environment anymore. Perception is the big challenge for that. And I think in terms of the robot, I think we have this. If we think about what we're trying to learn as not what the robot could do, but what the effect the robot should have on the environment, that's what's going to allow us to be portable across multiple different robot platforms. Because now all you need to know is whether the robot can take this action on this object, and then you have planning systems or other motion planning systems or other systems that can figure out how that robot should realize that effect on the object. And so if we're reasoning on the effects of the world, we will scale to many different types of robots. So I believe that I fully believe that creating general types of inference systems, general types of reasoning systems for mobile manipulation robots is within our grasp within the next, I'd like to say 10 years, but probably more like 25.
Okay, the next question is from Priti. We work on research hoping it will be put to good use in the long term, but how can one find opportunities in the short term similar to the shaving robot for Henry?
Great question. When you figure out how to do that, please let me know. I'm looking for answers myself. I think my understanding of how the collaboration with Henry, because it originally started from Willow Garage and Willow Garage, which is a robot startup company that came up in 2007 and lasted until about 2013. It was between them and Charlie Kemp at Georgia Tech. And so my understanding is that I know Willow Garage was founded by a billionaire who put in angel funding to make the startup go. And then they created this robot. Charlie showed it on CNN. They got a call from Henry, and then everything came together. And so there was a lot of serendipity there. But to me, I think the key thing is that it required a billionaire to you had a dream and created angel funding to make this happen. I worry that a lot of our federal funding, which is really the main engine of innovation, is maybe too conservative. It's sort of more following the trends of what already exists, as opposed to leading and trying new ideas. I think a lot of the reasons why I jumped at the opportunity to speak to the ACS community is I think cognitive architectures and the way we think about cognition computationally has just been neglected. I would love to see more funding of these ideas because you never know what the spark is that will create the next great idea and bring it into prominence.
Okay. The next question is from Shivali. I'm taking her sub-question, which is one of the reasons of harmful impact of AI tech that our evaluation paradigms are problem deployment agnostic. For example, accuracy metrics fail to incorporate the cost of failures. In a legal justice problem domain, cost of failures, such as a false positive leading to an indictment of an innocent person, would be very high given the rules of the justice system.
Right.
In other domains, cost of success and failures would look different. So I think she's saying that in most tasks we look at, all we care about is success,
right,
and we don't care about the cost of failures. And that ends up being problematic and when we put these things into society.
I could not have said that better myself. Because when we think about, if I went to CVPR or NeurIPS, 99% success on a data set is amazing. Wow, look, 99%, that's amazing. But if you happen to be in that 1% that gets it wrong, that's not very good. And actually, being wrong 1% of the time is actually not acceptable in many domains. And I think what we think of from a research perspective as what looks good or what are good results are not necessarily what it takes to deploy viable systems. And the concern is that we have we've maybe there's a lot of hype around these systems and around especially neural network systems, and they may be misleading, giving the public or the end user a false sense of security about how well these systems work. And neural networks are kind of a big regression black box. And so that there is real concern there. I personally worry, and it maybe sounds bad, that even though AI produces so much and it is very useful, the hype is so far exceeding what the systems can actually do, that we are in danger of having an AI winter if we're not careful. It's not an issue of technical capability. It's not an issue of making clear advancements. It's an issue of overhype.
Okay, thanks. So the next question is from Will Bridewell. With companies like Kindred fielding cluttered, pick-and-place capable robots in warehouses, when do you see academic research move beyond these sorts of tasks? Is there really more work to be done here?
I would say that I don't know Kindred, so I will have to look that up after our talk. I think the perception problem has become, the clutter aspect of what we're doing has been primarily a perception problem. And because companies and universities have thrown so much at this, that I don't think the cluttered aspect of what we're doing will be the main challenge moving forward. I think we have viable ways. It's still not perfect because, as Shivali said, 99% is not good enough if you're trying to run something on a production floor. You have to stop every once every 100 times a robot does something, you're not gonna be in business very long. But it will get better. The real issue is that how do we start to think about, if you're just thinking about pick and place tasks, we're gonna have that. There will be mechanisms in place. But how do you start to think about other types of affordances? The door handle that I have to reason about. I have to turn it and then pull it. The coffee mug, I have to hold it by the handle. It's not good enough to just pick it up in any form. How do I use a screwdriver? How does a robot understand what a screwdriver is and how to use it? And then putting that into the context where you can reason, where you can understand what the consequences of taking action with an arbitrary tool would look like. Those are the next challenges. So the picking and placing in Factory 4 is just one step towards being able to have general manipulation systems.
Okay, so I think we're essentially out of time, and it's too bad that we didn't get to questions about some of the other aspects of your talk, which was very thought-provoking. But people can go to